We're going to move on to talk about this idea of operator splitting methods. And so this is a commonly used technique in numerical solution strategies because it often tries to leverage some advantageous properties of parts of your PDE that you can have different schemes that are very well suited for one thing versus another. And so operator splitting methods allows us to take advantage, maximal advantage essentially, of different aspects of your problem that you're trying to solve. So let's talk about what it is. So it's all about exploitation of some of the physics that you're trying to model and leveraging different types of methods that are really good for different types of physics in some sense, or different kinds of behaviors out of the PDE. So for instance, let me give you this observation. Here's the first observation. If we are solving the one-wave equation here, ut equals ux, so this is wave behavior, what we found previously is that, for instance, a Ford-Euler scheme on this is unstable for all lambda. So and lambda is the CFL number. So if we're trying to solve this, the Ford-Euler schemes are terrible for this kind of behavior for wave equation. In fact, never stable. If we use leapfrog, then it's stable for lambda is less than or equal to 1. So in other words, if I'm going to solve this, leapfrog is the right way to solve this. Let's switch to the diffusion behavior. So if I have a diffusion equation, ut equals uxx, then Ford-Euler in this case is stable for lambda less than or equal to half. However, leapfrog itself is unstable for all lambda. So if I have these two schemes, Ford-Euler and leapfrog, they're kind of behaving very differently. So leapfrog works for wave behavior. It does not work for diffusion. Euler works for diffusion, not for wave behavior. So here's the question. What happens if I have this equation, ut equals ux plus uxx? So not only do I have wave behavior, I have diffusion. This is still a linear PDE. It's pretty simple. But when you start to look at the schemes we have here, forward Euler and backward Euler, both of them dislike one of these terms, right, in some sense. And so this is the problematic piece. However, each term individually can be solved nicely with the scheme here. So the entire idea that's going to happen here with operator splitting is to say, well, when I take a step into the future, delta t, how about I solve it first just the one-way wave equation, take a delta t step in that, and then take a delta t step forward with the diffusion, and that is my total delta t into the future. It's basically we treat each piece of this physics that they happen independently in time, but you advance each one of them delta t but separately. So that's the idea of what we would be exploiting in this operator splitting method. So how does this play out for us in reality? Well, let's take a little harder problem that we've been considering, right? This is the shallow water wave equations. What we have here in these terms, these are all my advection terms. These are my diffusion terms. So it's exactly what we're talking about when we talk about here, right? So this is my advection, that's my diffusion. It just now it's in 2 dimensions and a little more complicated and nonlinear as well. So when I have this, you could think about, like, look, what if I were to evolve the solution of this? First, I'll take a delta t step just with advection alone. And then I'll take a delta t step just with diffusion alone. So my initial condition comes into here. I evolve it delta t into the future. The output of this is now in here, and I take 1 delta t step with diffusion alone. Notice the advantage I have now. What I can come up with is I can come up with a scheme that is really well suited for advection in this step, and then change schemes that's well suited for diffusion in this step. So in some sense, like leapfrog this one, Euler step that one, because we already know that we have stability properties for those two kind of physics processes. So that's the key idea behind operator splitting. And it's a really key concept because oftentimes you do have numerical algorithms that are really well suited for one type of physics and not another. And a lot of the physics, more complex physics, has all of it jointly together, and this allows us to separate to take steps forward into the future. Okay, so exploit it. That's what we're doing. Take advantage of the best algorithm you have for each physics. So there's other advantages, however, to this operator splitting technique. This is the nonlinear Schrodinger equation. So it's IUT UXX mod U squared U. So this comes out of optical fiber propagation. So where the intensity of the light field is so intense that it induces a nonlinear refractive index change. And so this is where this equation comes from. And you can say, I want to solve it. It's a nonlinear PDE. But here's what operator splitting can do for you in this case. So first of all, I can break it up into two pieces. I can have this first step, which is essentially something like, so this is your dispersion that would be happening from the Schrodinger equation. And then here's your nonlinearity term. Now, so I take a delta step here and a delta step here. But here's the great advantage of doing this in nonlinear Schrodinger. I can write down analytic solutions for both of these. So for the first part of this, is all I have to do is Fourier transform it. In the Fourier transform domain, I can analytically solve this, and this is the solution. So I'm not even numerically stepping this anymore. I could just say, look, if I take a step in the dispersion term, I can just write down the solution over a delta t, analytically, right? So I'm not solving this ODE there. I'm just writing down the analytic solution. And now, in the second step, is this here. So for part 2, the analytic solution of that second solution is just this here. So for both pieces, so if I come back here, when I look at this, both these pieces have analytic solutions. So before, we were just trying to, figure out, can I get a good CFL here and a good CFL there with different schemes? Now I'm actually doing one thing further, which is I actually know how to solve it exactly. So why not just solve it exactly? And so my time stepping scheme is built from analytic solutions over delta t's, which are given by here. So that's a huge advantage, because now that's going to not only speed things up, I'm using the analytic solutions, and then everything comes down to just figuring out how to pick that delta t, because we still have now an error that's being picked up by treating each piece of the physics independently. Okay, so, but here's the algorithm for that nonlinear Schrodinger. You just start off, you first solve for the dispersion, analytic solution. The output of this over a delta t is now the input to here, to the nonlinear term, and I solve that over a delta t, and then now that's my solution, delta t into the future. Repeat. Okay. Here's the more general strategy you might look at, and this is what's called, what we're going to do is improve the scheme slightly by doing what's called Strang splitting. So you could take a delta t step in one physics and then delta t step in the other, or if I break this problem up into, let's say, two pieces, one piece is a linear piece, nonlinear piece, and say I break it up in this operator splitting way, what I'm going to do first is take half a step in the first term, a full step in the second term, half a step in the other term. This is called Strang splitting, and what it's been shown to do is cut the error down by a whole order of delta t. So you would always want to use this as your stepping scheme in operator splitting, because you drop your error significantly by an order delta t over if you just took delta t step in this, delta t step in that, with this splitting technique. So that's how you would actually impose this in practice. So operator splitting, if your problem is amenable to it, it's an amazing solution technique that it leverages quite a bit of knowledge in terms of the two pieces you might be doing the operator splitting with. So that's how you would think about operator splitting. Powerful technique, heavily used in different fields. But again, it's application specific. Some domains have a very nice splitting of the physics so that you can easily use this operator splitting technique to improve your solutions overall. So use it when you can.